1 minus q. What? Is that right? 3 q root of q. Yeah, okay. And we're asked to find the derivative, so p prime. All right. Number 17. This was the one you had? This is the one you wanted?
Yeah.
Okay. All right. So, groovy. Is it pretty?
No.
Can we make it pretty?
That's
What is
what I
it?
got caught on.
This is q to the 1 what?
1/3.
Yeah, so 3. There's that 3. Q to the 1/3 over 1 minus q. Right? Is this a product or quotient?
That is quotient.
Yeah, it's a quotient. So what's my u?
U is 3
Q to the 1/3.
whatever that is.
Yeah, and v is my denominator. So what's u prime?
1/3. It's actually 1 cube.
Is this 1 cube?
Well, how about q to the negative 2/3?
Yes.
How did I get that?
Minus 1.
Yeah, so I took the 1/3 and multiplied it by 3. What's 3 times 1 over 3? 1. And then 1 minus 3 is my negative 2. So that's my new exponent. Okay? And what's my v prime?
Just
Negative
1.
Negative 1. Plug and chug.
No, we don't plug into it.
Yeah, you do. You plug and chug. The formula is p prime is going to be u prime v minus u v prime
Yeah.
over v squared.
But I thought you didn't want us to simplify.
Well, no, you have to at least get to there, and then you're done.
It's like-
Finding the
because I would
derivatives
use-
of the parts is not
I would
enough.
do the, I would do the,
This
or
is
sinus
skill.
thing, and use the answer to
That's really
validate. Doing it
Yeah.
on the simplified version of it.
So that's why the name
I know.
is 1.
What did I tell you guys? Plug in a simple value like 1 into yours and into their derivative and see if they match. See if the slopes match. And if they do, you've probably got the same answer, right? Okay. Just in a different form. Does that help? Okay. Awesome. What's your name again?
Justin.
Justin. Okay. Frank, where was I? Oh yeah, 39. 39. Was this the cost benefit? All right, if the cost C in dollars of removing P% of the particulate pollution from the exhaust gases at an industrial site is given by, cost is a function of percent removed. Okay, is 8,100 P divided by 100 minus P. Okay, find the rate of change of C with respect to P. So what did I ask you to find? Derivative, is this a product or a quotient? Quotient. So what's my u prime?
100
81.
8,100. And what's my v prime? Plug and check. 8,100 negative 1. And then you just plug them into the same formula, u prime v minus u v prime. Okay? Groovy? How many of you guys are way overthinking this? Yeah. Okay. Awesome. That's good. Stop it. Stop it. Don't overthink them. Okay, 49. Was this candidate recognition? That's what's candidate recognition. Okay, awesome.
She's getting rid of the 100, right? That's why there's a negative. There's an imaginary 1.
Is that all that problem asked for? On a cost benefit? Yeah. Perfect. Okay. Awesome. All right. Candidate recognition. Suppose the proportion P of voters who recognize a candidate's name T months after the start of the campaign is given by P of T equals 13T divided by T squared plus 100 plus 0.18. Find the rate of change of P when T equals 6 and explain. I'll do that one. And the others you guys can do on your own. Okay. So find the rate of change of P when T equals 6. So basically we're asking ourselves to find P prime when t equals 6, right? So we need to find the derivative and shove 6 into it and see what happens, right? Okay, so let's go term by term. What kind of derivative is this?
Quotient.
That's a quotient. What about this one?
Product. No.
Straight derivative, right? And it's a constant, so what's gonna happen to it when we get to it?
It disappears.
It's gonna disappear. You're gonna kill it, killer. So now, my u is here, my v is here, my u prime and my v prime are, what, 13 and 2t respectively? Okay, so the derivative, p prime of t, is gonna be u prime 13 times v, t squared plus 100, minus u, 13t, times v prime, which is 2t, divided by v squared, t squared plus 100, quantity squared. Now what do I do?
Do you plug in 6?
Yeah, you plug in 6, and then once you get that, you're gonna get out a what? Because as a reminder, guys, plug an x into a function, get out a y, plug an x into any derivative, and you get out a slope. So what we're doing is we're evaluating what's gonna happen in the 7th month, right? Because remember, slopes are always run by 1. So we're seeing what happens if we go into the 7th month of the campaign, what's gonna happen to voter recognition? Is it gonna go up or is it gonna go down? Does that make sense? What do you guys think? 6 months, 7 months into a campaign, do you think it's trending upward or trending downward? Upward, but is it steep? Probably not, right? We get a big splash on like Pete Buttigieg, right, at the very beginning, and then we haven't heard much about him in the last couple months. So, does that make sense? So he's in the back of your mind, but you're not really thinking about him. Or maybe you are, I don't know. Maybe he's your guy. I don't know. He's not my guy. I'm kind of a Bernie girl. That should not be surprising. But anyway, or maybe Elizabeth Warren. I like her too. Yeah. Okay, anyway, so let's plug in the numbers and see what happens. So p prime of 6 equals 13 times, I'm going to skip a little, what's 6 times 6? So this is going to be 136 right here, minus, let's see, 13 times 2 is 26 times 36, because that's t squared. T squared is going to be 36, divided by 136 squared. That's going to make my life a lot easier. Let's see, 13 times 136 minus 26 times 36, divided by 136 squared. Okay, 0.04498. So let's read the statement of the question again. This is why I don't want you guys to simplify. Isn't it easier just to plug stuff into this? Why on earth would you simplify it, right? Because in the real world, we don't stop here. We plug numbers in and analyze them, right? So there's no sense in like simplifying it. Doesn't make any sense. Yeah. What's that?
You're probably right, but when you went 13t times 2t,
Mm-hmm.
how is that 26 times
Ah,
36?
what's 13 times 2?
26.
26, and t squared is gonna be 6 times 6, right? 36. So there's my 26 and my 36. So all I did was I just distributed it really quick in my brain. Does that make sense?
Yeah.
Awesome, okay. What the hell was I doing? 49, that's right. Okay, support portion P of voters who recognize a candidate's name T months after the start of the campaign is given. So find the rate of change of P when T equals 6. So this is a proportion, it's a percent. So going into the 7th month, that's really squeaky. Going into the 7th month, voter recognition of the candidate will increase by 4.5% approximately. Okay. Does it make sense? Yeah.
So it's not the 6 month?
No. Yeah, because remember, this is always divided by 1. So when we plug in 6, we're going over 1 month, and we're going up in proportion by that. So over 1 month from 6 is going into the 7th month, right? And this is the proportion increase of voters who recognize the candidate. Does that make sense?
Yeah.
Always by 1. So no matter what your number is when you're interpreting it, just add 1 to it. If you plugged in 150, you would say at the 151st, blah, 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 blah. It's going up or down by blah, 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 blah. Ruby? Okay?
So there's no negative number, that's why it's increasing.
Yeah, it's increasing, but nominally, right? 4.5% is not tremendous. But after 6 months of campaigning, it wouldn't be tremendous.
Yeah.
Because pretty much everybody that's gonna hear about that person will have heard about that person already.
So voter fatigue.
Yeah, kind of, voter fatigue, or saturation. Another way to look at this, guys, is market saturation. Don't think of it as a candidate so much as an advertisement for a product, right? When it first comes out, it makes a big splash. I don't know, that's something I can think of. iPhones. And then after a few months, what happens to the demand and the chirping and the talking and the tweeting and it slows, right? So that's what's happening, is we're hitting some kind of saturation point. Candidate recognition is gonna do this over time. Same thing with anything that you're selling, because you're essentially selling a candidate when you do an advertising campaign, right? It's the same thing. So what we're seeing is really nominal slopes at this point instead of really sharp slopes. If I were to do P equals 1 or T equals 1, I would see a much larger proportion here because it's gaining in leaps and bounds at the beginning of the campaign. Does it make sense? Awesome. Okay. So does me talking through these help you guys a little in understanding what we're doing in these application problems? Okay, awesome. Okay, I'm tired of Coldplay. I need something else. Coldplay. It's stuck in my brain.
I was gonna bring back.
How about Jimmy Buffett?
No, that's worse.
The other one.
Parrot heads can just like
System of a Down?
bury your parrot heads in the sand.
Oh, System of a Down.
That's what it was.
Parody heads.
System of a Down? No?
What? No?
Trust
Oh,
them.
that would be all right.
Yeah.
You just went from one extreme to another.
I'm a man of many.
Many interests.
Sure. I couldn't think of the word.
Okay. All right. Let's tackle some chain and power rule today. That was fun. Inch nails, that's what my brain's gonna do today. Can't stick it out loud though. It's kind of violent. All right.
I'm going to be.
I'm a 90s kid, what can I say?
Well, I was born in the 90s, so technically I too.
There's a very small, well, actually not so small, little goth living inside of me going, let me out. Let's go to the graveyards. Seriously. 9.6, chain and power rule. So up until now, it's been kind of
Nice.
nice, right? Today
I
it's a
don't like
little
that.
tougher. Yeah, nice. Here's the thing, guys. This is not mine either. Here's the thing. Calculus is kind of like onions. There's a right way to cut them. There's a wrong way to cut them. If you cut it right, you'll be okay. If you cut it wrong, you're gonna cry a lot.
Like you cry either way.
No, you won't cry. No crying. No crying. Just come visit me. I have tissues and chocolate and tea and cozy places to cuddle up and cry. That's cool. Seriously. I mean it, guys. Chain and power rules. What we're doing is we're looking at nesting functions today. Okay? So let's take a look at this one. f of x equals 3x squared plus 2 to the 5th power. Now, up until now, you don't have a way to solve this. Excuse me, you don't have a way to take a derivative here, except by foiling this beast out, and boy, oh boy, it would be beastie, wouldn't it? If we FOIL this out to the 5th power. I have a little thing for you guys, though. There's a way we can tackle this, but first I gotta teach you the fugly way. And then I'll teach you my way. So walk and then run. Groovy? So here's walking, bear with me. What is f a function of? I mean, what's its input variable? X. We're gonna change that. Let u equal x squared plus 2. Now, f is a function of u. Fu 3u squared. You guys with me? And then u would be a function of x, wouldn't it? Because u has an input variable of x. So u is a function of x, and that equals x squared plus 2. So I'm just rewriting what I did in green. So far, so good?
Would it
Yeah.
be 3u to the 5th?
Oh yeah, it would be to the 5th. What's your name?
Ryder.
Ryder, with a Y?
Yeah.
Thank you, Ryder. Everyone wins. Oh, it's not a J. Ryder. Awesome. Extra credit for you. Good job. So now, I have a nested function. I have a function within a function, right? You guys remember this crap? Those of you that took finite, those of you that took college algebra, you both should recognize this. These are those nested functions. F inside or outside of G, I can never remember. You don't have to remember, not in here. Good times. Let's take the derivatives of these. But let's keep them real formal-like, okay? So the derivative of f with respect to u is gonna be what? Don't overthink it.
15u to the 4th.
15u to the 4th, right? And what's the derivative of u with respect to x gonna be? Don't overthink it. 2x. Now we smash them together. So if I multiply this and this, I'm gonna get this. The derivative of f with respect to u times the derivative of u with respect to x is gonna be 15u to the 4th times 2x. Is that right? Yeah. Well, what was u again? U had a value, so we're just gonna back substitute now. So that's actually 15 times u was x squared plus 2 to the 4th times 2x. And there's something I want to show you. This was in terms of u and x, yeah? What's this all in terms of?
X.
X, that's our input variable. Check this out, guys. Did you know you could do that? The du's cancel, leaving us the derivative of f with respect to x. So x is our input variable, x is our input variable, and we're back to taking the derivative of the whole thing. And that's our final answer. I could simplify it a little bit by taking the 2x and multiplying it by 15. So I would get 30x, open x squared plus 2 to the 4th power. And then I'm done. And that's the derivative. So I'll let you guys stare at that for a second. I know you don't like it. I've had years of people not liking this. I get it. There's an easier way. Gesundheit. Because this is a complicated central step here. Rewriting something in terms of another variable, creating an entire new set of functions, taking the derivatives of both, and then smashing them back together. It's kind of like splitting an atom and then recombining it. It doesn't feel good. It's not really a good thing.
I'm kind of lost how you went
Yeah.
from f of u to u of x.
Aha, okay. So f of u means that u is my input, right?
Right, yeah.
So that makes sense because u is just u.
Right.
U of x is a function in terms of x. X is its input.
Okay.
So that's where that comes from. Okay, so we have a function inside a function essentially, where u is the function inside of f.
Okay.
Yeah.
Where's the 30x come from?
Aha, okay. So I have 15u to the fourth times 2x. That's 15 times this. So I just move the 2x over and make it 30x. Okay? Because a times b times c is equal to c times b times a is equal to a times c times b. Anyway, multiplication, you can move stuff around, right? 3 times 4 equals 4 times 3. Okay. Let me show you a faster way. You have an outside function. What is it? 3 jump to the 5th. We're going to start with the outside layer and peel it. And as we peel, we take derivatives. So what's the derivative of 3 jump to the 5th? 15 jump to the, what was the jump? Just x squared plus 2. So that's my outside layer. Notice I only touch one layer at a time. Think of it as, you can't take your underwear off before you take off your pants, right? Seriously guys, keep it clean, but really, unless you're wearing your underwear on the outside, you can't take those off first. You have to start with the outside layer. That's what we're doing here. We're taking off the outside layer, and the outside layer is this 3 times stuff to the 5th. Now when I peel that off, I'm left with x squared plus 2. What's the derivative of x squared plus 2?
2x. Line 2x.
You're done. I just peeled from the outside layer to the inside layer. That's it. I skipped all the renaming stuff. I went right to the goodies. That sounds bad. I went right to the good stuff here. That's where I ended up, isn't it? 15 times x squared plus 2 to the quantity to the 4th times 2x. That's it. Memo, you don't look happy.
Good, it's too much.
No, I know.
What's- You're not happy? What's going on, man?
I don't get it.
How do you get the 2x
Yeah.
Ah!
on the end?
How did I get the 2x? I peeled. So when I'm working with so listen to this guys, listen real carefully. When I'm working with the outside layer, no touching the inside layer. Only touch one layer at a time. So when I'm working with the outer stuff outside of the parentheses, I'm not gonna mess with this, okay? So that's just gonna get carried along for the ride. So when I take the derivative of 3 jump to the 5th, I'm gonna peel. I'm gonna peel that stuff off until I'm left with what's inside of the parentheses. And then I take the derivative of that. And that's where that came from. Yes, Helena.
Like, why do you keep both for the derivative and the derivative of the x squared plus 2?
Why do I keep,
Well, yeah, you add the 2x because that's the derivative of x squared
Mhm.
plus 2, right? Why-
careful though, I multiply, I don't add.
Yeah.
Okay.
Yeah. Why is the x squared plus 2 still there?
Ah, it's in here because we were working with the outside layer on this step. We don't touch the inside layer, it moves along untouched. Then when we peel the outside off, then we tackle the inside layer. So I call this the derivative of the outside, d out, and the derivative of the inside, d in. D out, d in. You guys are gonna hear me say this all semester long. So before, we had, what was it? 3? That was a 3, wasn't it?
Mhm.
Yeah. 3 and to the 5th. Okay. So once again, I think of these parentheses as a bubble that sort of protect the inside function. When I'm working with the outside function, I only work with the outside function. I don't touch the inside. Conversely, when I am done with the outside function, it's peeled away, it's gone, I don't need it anymore. The derivative of the inside is gonna be 2x. I'm gonna show you guys a lot of these. I'll leave this one up. Hopefully, this will make a little more sense once you see the pattern. I think you guys are gonna like these a lot more. Okay.
So that's the.
3x cubed plus 6.
Yeah. And I was like, what's down? Right.
Okay, guys, what's the outside layer? 8 junk squared, right?
16.
So the derivative of the outside is going to be the same thing we've been doing all along. 2 comes down. What's 2 times 8? 16 junk. Right? 2 minus 1 is 1.
One. All right.
Memo,
It's
Memo
early.
needs coffee.
Yeah.
And now we're going to peel it. We don't need the outside layer anymore. We took its derivative. We're done with it. 1 layer at a time. When you're messing with the outside layer, you don't touch the inside layer, do you? Just 1 layer at a time. Okay? Yes.
Why is that not a negative 16?
Why is it not?
Yeah, because if you do negative 8 times.
There's no negative 8, honey.
Oh, that's the equal sign? I
Yeah.
literally am blind right now.
That's okay. Are you all right?
Yeah.
Okay.
That literally looks like a negative. It's fine. I'm just blind.
Okay, let's try another. The more you see, guys, the more you see.
I feel so stupid. I just said. You're like, I always see perfect.
Is it pretty? Nope. What makes it pretty? I hear an awful lot of, I'm burning her, I'm so burning her. What's my inside function? X cubed plus 10x squared. And that's all gonna be to what power? 1/2, yeah. Because again, you guys, it's the same process, isn't it? Whatever's under here gets an exponent, right? And then your power becomes 1/2 up here. Okay? So now what's my derivative? Peel. 1/2 comes down. Do I touch the inside? No, because I'm working with the outside. 1 layer at a time. What's 1/2 minus 1? 1/2. Now, what's the derivative of the inside? Peel off the outer layer.
3x squared.
Yeah. Done.
I was doing them one at a time.
1 layer at a time.
Yeah, the first one. but
That's
I was
good.
rewriting it.
Oh, you were.
Yeah,
I
that's
see.
so easy.
No worries. What do you guys think? You starting to see the pattern here? Whatever's in the parentheses gets left alone for the outer layer step because it's your inside function. Think of this as like a warm little blanket, wrapping it. We have to peel the outside before we tackle what's inside the blanket. Ruby? That's all there is to it. That's the chain and power rule right there.
So,
Yeah.
so when you have like an equation like that from the beginning, the first step you want to do is convert it into.
Always get it into that AX to the N form.
Okay.
And did you guys know we've been doing this all along? You didn't really think about it, did you? But check this out. If we had a function that was like, say, 3x to the 5th, let's do d out dn on this. Our inner function is just x, isn't it? It's like this, right? So what's the derivative of the outside? 15x to the 4th, right? Because you don't touch the inside layer. Now what's the derivative of x? We've been doing this all along. We've been doing d out dn all along. You just never thought about it because the inside function's derivative is always 1 when the inside function is x. When it's more than x, you have a little more work to do. But it's a natural progression from what we were doing before. Does it make sense? Give me a thumbs up if you're good. Give me a slightly shaky one if you're not so good. Okay, awesome. All
I
Alright.
would probably have to work on that one, the first level, to rewrite it correctly.
To rewrite it to an
So that I
exponent?
could
Yeah.
save time on that.
Awesome. Okay, well, let's practice those, shall we?
I just don't like when towns have the roof. I don't like this.
Somebody asked me when we were first getting started about something that looks like this. F of x equals 4 over, let's go 4 over 9 times 3x to the 5th. So now when I grab that exponent and bring it up, what goes with it?
A negative
3x. So if I rewrite this, this is 4/9 times 3x to what power, guys?
To -5.
-5. Great. Now what's my derivative? Peel.
So 29.
Kind of 20. Good. Good. Times 3x. No touching the inside. To what power?
-6.
Good. Times the derivative of the inside, which is? Good. Done. Yeah? In a good way? Yeah? Yeah! That's teacher crack. I need more.
So when you do the exponent, when you got 20 minus 20, you didn't touch the denominator. You just, that's where I would have made my mistake. I would have,
Ah, but when I
multiplied.
bring that -5 down, let me show you what's happening between this step and this step. When I bring the -5 down, I'm actually doing -5 over 1 times 4 over 9. Right? That's what this actually is. So I'm just bringing this down as a fraction and multiplying it to my other fraction. Right? -5 times 4 is -20. 1 times 9 is 9. So if it helps, think of your exponent as a fraction all the time. Okay? That way you know which layer goes with what. How many of you write all of this in one tiny little line? You write all teeny tiny. Don't lie. Come up. Stop it. Stop it. Because we're gonna get to the point where we're gonna have multiple layers. As it is, we have 3 layers, guys. We have a denominator, a numerator, and an exponent. Don't confound which one is which, because in just a couple of sections, we're gonna be working with layer upon layer upon layer upon layer. And you're gonna wanna know which one goes where, okay? So write big. Write big. Take a line for every layer. Yeah.
Where do you get the 3 at the end from?
Ah, the derivative of the inside.
Okay, that's just.
So the derivative of the outside, no touching the inside. Once I'm done with that, peel, derivative of the inside. Okay? Awesome. Let's do another.
Oh, that's why she said meow. This is like meow.
Ah, frickin' Coldplay. I like this one. Now, there are 2 ways you can tackle this. One is the quotient rule. How many of you saw a quotient? Cool, that's okay. But what's your u prime gonna be?
1.
Careful. 0. So when you take the derivative of this 4 and your u prime goes to 0, remember that any term that's multiplied by 0 is gonna end up at 0. So let me do it the quotient way. And then I'll do it using the power rule. So this will be u prime, so y prime equals u prime is 0 times v, 10x cubed plus 5x plus 2 minus u times v prime divided by v squared. Now, what cancels?
First, yeah.
That whole thing, because it's multiplied by 0, right? Okay, so I want you guys to keep this in mind, because I'm gonna do it using the power rule now. And you might find that it's easier. You might not, whatever floats your boat. It's cool. Sometimes there's multiple methods that work. So let's rewrite the exponent, or let's rewrite this sucker. I'm gonna give it, I'm gonna wrap it, that's what I call it. I'm gonna wrap it with a power. What's my power? So when I drag that power up, what does the sign become? Good. So now I have 4 10x cubed plus 5x plus 2 to the negative 1. Now I can do d out dn. What's the derivative of the outside, guys? Negative 4 junk to the negative what? 2?
3.
Negative 4 junk to the negative 2. Now what's the derivative of the inside? I'm going to peel the outside off. What's the derivative of the inside?
30x
30x squared plus 5.
Plus 5.
What happened to the 30x squared next to 4?
Look at it. Look at it, Maria. This is a negative 4 times the 30x squared plus 5. Negative 4 times 30x squared plus 5. This is a thing times a thing times a thing. That's just like saying this times this. And then if I drop this downtown, I have that to the second power. It's the same answer in different form. I'll let you guys stare at it for a second.
So you just left it alone because in the end the bottom one would be the same as that.
Uh-huh. Yeah, if I drop this downtown, I'll rewrite it. And it'll be just like this one, guys. Y prime equals negative 4 times 30x squared plus 5. So I'm going to leave those elements on top. And on the bottom, I'm just going to drop that negative 2 factor down and make it positive. And now I'm left with the exact same thing. You guys see it? Which one do you like better?
Power.
Power? You like the power roll? Makes you happy. You like peeling layers?
Yes, I do.
You must like onions. I love onions. They make me happy.
I love onions.
Yeah, they rock. They're like the base of everything delicious.
The only thing that I'm struggling with is like, you got the bottom that you brought up.
Uh-huh.
And then when you brought it up and you did the derivative,
Uh-huh.
so you
Like
did the
from here to
pulling
here?
out, yeah. And
Okay.
so when you brought the denominator up, which is the second line,
Uh-huh. Right here?
yeah, no, the second.
Oh, the second line. This is the derivative, honey. This is the same as this, just rewritten. I just dragged the exponent up and took the base with it.
Oh,
Okay? Then I perform the derivative.
oh, now I
This-
see it.
This is d out,
Okay, now I see it.
and this is d in.
Okay.
And over here, we had u prime times v minus u times v prime over v squared. So 2 different methods gives us the same answer. So you just find the one that's most elegant for you. Find the one that floats your boat, blows your hair back, runs your bike.
So it doesn't matter which way you put u prime to v or vice versa, because in the book it's vice versa.
No, it's not. Careful. It's
Because all of
not.
my answers were backwards.
They might do v prime times u
Mm-hmm.
instead, but like this, they might do
Yeah.
v prime times u.
Yeah.
But they're not confounding these two. A minus B is not the same as B minus A. They might confound these guys inside of this formula, but they will not switch the two groups. I promise.
Yeah, because they were backwards.
I promise. Yeah.
They were the
So
same, just.
they were the same inside these, just switched, right? This one might have been switched or this one might have been switched, but I promise you this collection of things came first in the formula. Always, always, always. Okay? How do you guys feel? Questions? Talk to me. Memo.
Yeah.
Yeah.
Sorry, could you
It's
just
okay.
explain how you got from the second
This one
to the third?
to the third?
That's the third
Okay,
step, yeah.
so recognize I have three things being multiplied here, the -4,
Mhm.
all of this stuff, and all of this stuff. So all I'm doing is I'm yanking this downtown, right? I'm just taking this directly downtown, and what's left on the numerator is this times this.
Okay.
That's all I'm doing. So I pulled this down, and I left the -4 and the 30x² + 5.
Oh, to get rid of that negative exponent? Or-
Yeah, to get rid of the negative exponent, and to show you that it's exactly like this.
Okay.
Yeah.
Can I test you, or want us to break it down?
No.
Okay.
No, I'd be excited if you got here. That's as far as I need you to take it. Yeah. Again, I'm testing you on the mechanics, not how pretty you can make it at the end. Okay? How do you guys feel?
Can we do another one?
Yeah, absolutely. We got 10 minutes, and then I'm gonna give you guys one to work on yourselves. Okay. Actually,
This paper that's not even-
I want you guys to try something now. I'm gonna put you in groups. If you're already at a table, no stress, just stay there. Groovy. If you're solo, partner with like somebody here, like those two partner together, you guys partner together, you two partner together. And yeah, actually, could you three partner together, or you just turn around and partner with the three behind you? Will that work? Okay, so you two partner together. Everyone else has a partner at their table? Fabulous. All right, here we go. I'm gonna write down a bunch of functions, and you guys are gonna work together to take derivatives. So much fun. So much fun.
I was like, bro, I
She has
can't.
these little flowery outfits, and I come looking like a bum every day.
I was gonna be coming along today. I just started feeling
I woke up at 6:15, like all night. I couldn't think of it. It was like 9 a.m. and it was 4 in the morning. I woke up at like 4 o'clock.
But how would you think it's 9? It's dark.
Exactly. I was like hallucinating this morning.
Oh.
It was dark. I'm like, I missed it. I don't know what to do. Okay, we can't write all these down because we need space to. Y'all are just going for it.
It's the best way to do it. Just
So 4 times 5. Remember outside there. You did it, yeah. Okay. So
All right.
inside.
I'm gonna come around and help you. Yay! So excited.
I think I'm doing it right or something. I don't know where this thing goes. But yeah, don't do whatever you want.
Right, well, she was saying like this is 20, and then this would be 3
You don't
x
do anything to that,
squared
right? For the
plus
moment.
10x minus, yeah,
Wait, I thought you left that alone. Then you just do this one.
right. So we did that.
You do this, and then you
That was the
rewrite
outer
it.
layer. Then this is the inner layer.
Oh, you rewrote it already. Okay, this is the next one. I thought the inner layer was next to the outer layer.
First two times was the same.
How's Brenda doing?
Yeah, you touch that side until you're done with the outside.
Brenda? Oh, you said Brandon.
How's Brenda doing?
I don't know. I need her.
Should I stop recording?
Yeah.